This is very common question. You can see people will ask generally in the question for unbiased estimator that show that the sigma square x is unbiased estimator of sigma square. So let us do this. All right. Okay. Let's change the color. All right. Fine. So because we are dealing with the unbiased estimator here, so we just quickly see the unbiased definition of unbiased estimator what we have here. Okay, so if you can see here, an unbiased estimator of a population parameter, its population parameter is the estimator whose expected value, this is important, whose expected value is equal to that parameter, right? So I have to take the expected value of sample. I have to take the expected value of the sample and make sure that that should be equal to the population parameter. For example, in this case, I have to prove that sigma square x bar, which is expected value, I have to take this and I have to make sure that this is equal to sigma square. So sigma square x bar is the variance of the sample and sigma square is the variance of the population. Parameter means for the population and the statistic is for the sample. We have seen that. So expectation now we have to deal with. So this is what we are going to do here now. So I have to prove, I will just write it here. So I have to prove that the expectation of sigma square x bar, which is from the sample, variance of the sample, should be equal to sigma square. This is what I have to prove. All right. So before I go ahead, let us recall few things which we have done in the expectation, earlier. So we know that the expectation of x is equal to mean. I'm recalling this from the chapter expectation, what we have done. All right. We also know that the variance of x is equal to e of x square minus mean of or expectation of x whole square, right? So if you want to find e of x square from here, so you have to take e of x square is equal to, bring this side. So this will become the variance of x plus the expectation of x whole square. Okay, so this will become the variance of x means nothing but your sigma square plus expectation of x is mu, so this will become mu of whole square. So this is we have here now. So if I want to write this for sample mean, if I want to extend this for a sample mean, extend this for the sample mean. So your expectation of mu of x bar square, I'm just changing the notation here now. Here it was x square, now x square will become the mean of sample. So this will become your sigma square of x bar plus your mean of x bar. I'm just writing this notation in that form of sampling distribution of mean. I'm just changing the notation. All right. So this implies sigma square x bar. We already know this means this is sigma square by n, and mu of x bar is always equal to mu. So this will become mu of whole square. So this is small part which we may use this portion, this one and this one in the derivation. So kindly note this part. So this is this thing which I have taken the expectation part. Or Now let us come back to this question. So the expectation of sigma square x bar, the formula we have already seen. We know the formula of x sigma square x bar. So this will be nothing but your expectation of, this is a variance. So variance is always the data vary from the mean. So this will be whole square divided by n minus 1, and this is obviously I from 1 to n, small n, because it is per sample. Okay, and because it is unbiased estimator, I have used here n minus 1. If I use n here, then I'm talking about biased estimator, but in this case I'm talking about unbiased, so this will be n minus 1 here. All right, so next, this will be expectation of, I will square this up and try to split this. So this will be summation of xi, this will be a square minus 2 times a into b plus b square. All right, so this will be b square, and 1 by n minus 1 I will write outside, or I will just write with here only n minus 1, doesn't matter. Okay, now this equals to the expectation of, I will write each term now. This will be summation of xi square divided by n minus 1 minus, now you can see that 2 and sigma, mean of x bar is the constant term. Mean is constant, 2 is constant. So when you take summation, these two can come outside. So this will become 2 mu x bar, summation of remain with xi here, divided by n minus 1, plus when you take summation with this particular term, again you have mean, which is a constant term. So this will come outside and remain with summation of 1 divided by n minus 1 in this case. Constant term can always come outside the summation. Okay, so this gives me the expectation of summation of xi whole square divided by n minus 1 minus 2 mu x bar. What is summation of xi? Right? What you can write summation of xi here? If you just recall the formula of mean we can always write that as summation of xi divided by n. I want summation of xi, so you can bring this side. So summation of xi can be written as n times mu of x bar. All right, so now I will substitute the summation of x value as n times mu of x bar here. So this will become n times mu of x bar and whole divided by n minus 1 plus mu x bar whole square. Summation of 1 means 1 plus 1 plus 1 plus 1 up to n times. So this will become n here. So this will be n divided by n minus 1. If any step you have a doubt, please let me know. All right. Okay. So this implies this will be expectation of summation of xi square divided by n minus 1 minus 2 times mu of x bar. Mu of x bar become mu of x bar whole square. So you have n also here. Then you will become mu of x bar whole square whole divided by n minus 1 plus n divided by n minus 1 into mu of x bar whole square. Okay, so now we have minus 2 n by n minus 1 mu x bar whole square, and we have n by n minus 1 mu of x bar whole square. So minus 2 plus 1 time. So when you subtract this term and this term, minus 2 plus 1 become minus 1. All right. So I will take this to the next slide. So this will become the expectation of sigma square x bar becomes what we have. Okay, this will be expectation of summation of xi square, I guess, xi square divided by n minus 1, then minus 2 plus 1. You can see n by n minus 1 mu x bar whole square is common anyway, so minus 2 plus 1 become minus 1. So this will be minus of n by n minus 1 mu of x bar whole square. Only this term is remaining, right? So minus 2 n by n minus 1 plus n by n minus 1. So become minus 1 time n by n minus 1, right? Mu of x bar whole square. So now we can write the expectation of each term. So this will be expectation of summation of xi square divided by n minus 1 minus expectation of n divided by n minus 1 into mu of x bar whole square. 1 by n minus 1 is constant term, so can come outside the expectation. So this will be expectation of summation of xi square minus x. Here also n divided by n minus 1 will come out and remain with the expectation of mu of x bar whole square. Now we have the term here expectation of xi square or x square, whatever you say, it's a data point, and we have expectation of mu of x bar whole square. So we have derived this short formula here. You can see I have expectation of x square value as sigma square plus mu square, and expectation of mu of x bar whole square is this term. So I will substitute this and 2, equation number 1 and 2 here. All right, so this turns out to be your 1 by n minus 1, and this will be turned out to be your summation of sigma square plus mu square minus n by n minus 1, and expectation of mu of x bar is nothing but your sigma square by n plus mu square. So now we have to just sort this out. So 1 by n minus 1, if you take summation of sigma square plus summation of mu square here minus n by n minus 1 sigma square by n plus mu square. So when sigma square come outside the summation, this will become n times sigma square. When mu square come outside the summation, becomes summation of 1 inside, so become n times mu whole square minus, I will multiply this inside, so this will become n by n minus 1 sigma square by n plus into minus is minus, so this will be minus n by n minus 1 times mu square. So this also I'll multiply and check what we will get. So this will be n by n minus 1 times sigma square plus n by n minus 1 times mu square minus n by n minus 1 sigma square by n minus n by n minus 1 mu square. So these two terms get cancels out. We remain with these two terms. So I will write it here. Okay, I will just draw one slide. Right. So we will remain with n by n minus 1 sigma square minus n by n minus 1 sigma square by n. So I can take sigma square common. So remain with n by n minus 1 minus n by, this get cancels out. So remain with 1 by n minus 1 times sigma square. So n minus 1 is anyway common here. Numerator also will get n minus 1 times sigma square. This get cancels out. So we will get sigma square. So now you can see that we have got expectation of sigma square x bar as same as sigma square. Because I have taken n minus 1 and this is for unbiased. So if any doubt in this derivation definition we want, so for an unbiased estimator is said to be consistent if the difference between their estimator and the target population parameter becomes smaller as we increase the sample size. For example, for unbiased estimator, you know that your mu of x bar is equal to mu, right? So, and this is said to be consistent if the variance of x bar, that is nothing but your sigma square x bar, which is nothing but your sigma square by n. So in this term, when you take n value larger and larger enough, then what will happen? Your sigma square x becomes smaller and smaller. So if you want to check whether your sigma square x bar is consistent or not, you have to take the n value larger and larger. That is what consistency means about. All right, efficiency. If efficiency has to work with the two unbiased estimator. So if we have a two unbiased estimator for a population parameter, it can be any parameter, mean or variance, then we say that estimator with a smaller variance is more efficient. If we have two unbiased estimator, if we have two population parameters, sigma 1 square and sigma 2 square, whichever sigma square has smaller value, that sigma 1 square is more efficient. So you have to look for the smaller variance. That is the meaning of efficiency. The only definition you have to look at. Now, the last topic of this chapter is maximum likelihood estimate. Okay, this is also a one type of estimation which we're going to do. So before I like to tell more about maximum likelihood estimator, I've just taken an example and let us understand what maximum likelihood estimator works about. So in maximum likelihood estimator, you will be having a set of independent data taken from the population. In the initial class, as I've told you, whenever we have a population, okay, whatever this population has, how many number of data points does not matter. This population has some kind of distribution. This follows some distribution. This population data set has some kind of distribution. The distribution can be uniform. The distribution can be exponential. The distribution can be maybe binomial or maybe Poisson. Any distribution it may follow. But when we apply the central limit theorem, the all distribution will converge to normal distribution. We have seen that. But now in maximum likelihood estimator, if we have certain data taken from the population and we also know their distribution. So for example, in this case, I have taken a Poisson distribution because this data set has taken from the Poisson distribution type, and Poisson distribution we already seen always represented by this formula P of X. Now we have to find the maximum likelihood estimation of parameter M here. So maximum likelihood estimator is a type of estimator which estimate the parameter of the distribution. If you look at the P of X, I have only one parameter M. So I have to just find the maximum likelihood estimation of uh, M in this case. So how do we go ahead with this sort of data set? So if we have a X value given, which is a Poisson distribution, e power of minus m into m power of x by x factorial, right? We have to find the maximum likelihood estimator. So maximum likelihood estimator is represented with L, and for which parameter I am finding, that parameter I will write. So this is nothing but your probability of x is equal to whatever the data set we have given. We'll just substitute that. So x is equal to 5. But in this case, you will not get into, you have to take the product. So this will be probability of x is equal to 9 into probability of x is equal to 3 into probability of x is equal to 12 into probability of x is equal to 14. So when you substitute this in P of x, you will get e power of minus m into m power 5 divided by 5 factorial into e power of minus m into m power 9 divided by 9 factorial into e power of minus m into m power 3 by 3 factorial into e power of minus m into m power of 12 by 12 factorial into e power of minus m into m power 14 by 14 factorial. So this is your likelihood function. So this likelihood function is all depend upon the probability distribution, what you know. So now when you take the product of all this, so if you can see your e power of minus m into e power of minus m into e power of minus m is multiplying how many times? 1, 2, 3, 4, 5 times. So this will become e power of minus 5 times m into m power 5 into m power of 9 into m power of 3 into m power of 12 and so on. So 5, 9, 3, 12, 14 will add up. So when you add all this, you will get m power 43 whole divided by 5 factorial into 9 factorial into 3 factorial into 12 factorial into 14 factorial. So this is your likelihood expression or function we have got it. You have to find the maximum value of the likelihood. So if you have any function like this, so you have two type, which is the maximum value of this function. Definitely the second, this quotient is actually a maximum value, right? But to check whether this is a maximum value or not, okay, if suppose this is y or x, y and x, so we have already seen that how to check whether it is extreme value of a function or not. We always differentiate with respect to x and we will equate that to 0. Okay, and if we do this portion, we will get the maximum value. But it may be a chance that we may get a local maximum, we may get this value also. So to verify whether it is a maximum value or not, we will differentiate this second time and check whether this is negative or not. If the second derivative is negative, if second derivative comes negative, then we can conclude that your dy by dx value, whatever you have got after equating to 0, is a maximum value. Okay, so now you understood that we have to differentiate with respect to something to find the maximum of this likelihood function. This is called as likelihood. This is called as likelihood function. All right. So because we have a lot of e power and m power 43, so get rid of this power. I will take the log both side first. So I will take the log base e of the likelihood function I will take log base e both sides. So this will become log of base e itself, e power of minus 5m into m power 43. And this is log n by log n minus log of 5 factorial, then we have 9 factorial, and so on up to 14 factorial. So now I will differentiate this L with respect to the parameter you are finding. The which parameter you are finding here, that parameter with respect to only have to differentiate. So to differentiate this with respect to m, what you'll get here. So before I'll differentiate, let me rearrange the terms. So here you will get, if you multiply, you will get log m into log n. So log m plus log n. So you will get minus 5m. Log e into log e get cancels out, plus 43 log m minus log of 5 factorial into 9 factorial and so on up to 14 factorial. This is a log likelihood function. So now I will differentiate with respect to m. So when I differentiate with respect to m, you will get minus 5 plus 43 into differentiation of log m will be 1 by m and minus 0. And now equate this differentiation term to 0. So when I differentiate this term equal to 0, what you'll get? You will get minus 5m, minus 5 plus 43 by m is equal to 0. So what is the m value you will get here? You will get m value as 5 by, 43 by 5. So here I have got the maximum likelihood estimator of parameter m, which is for Poisson distribution. If you just look at the value of m, what you have got here, your value of m is nothing but summation of all this term, 5 plus 9 plus 3 plus 12 plus 14. So this is nothing but your summation of all data set divided by 1, 2, 3, 4, 5, total number of data. So this is in general form. So whenever you have to find the maximum likelihood estimator of Poisson distribution, we always get this particular value in general. So you take any data set here and you apply this formula, you can get m value. So why to do this maximum likelihood estimator? Because I'm dealing with unbiasedness in this case. So the sample which you have taken from the population is unbiased, and if you don't know the parameter value of that, you can find out the parameter by using this set of formula. Anyway, let us go ahead. So now look at the definition of maximum likelihood estimator. We will be having set of n independent data. This should be given to us. We also know the type of distribution from which this n set of data is taken. As in previous case, we had Poisson distribution given. So data will be given to us, distribution will be known to us. So which will be in the form of f of x comma theta. Earlier I have taken p of x, now I have taken here f of x comma theta, where theta is the parameter. For which I have to find the maximum likelihood estimator. This theta will vary as per the distribution. For Poisson, theta was m. For normal distribution, that can be mean and sigma and so on. We will discuss that. So now we have to find the maximum likelihood of parameter theta. This theta will vary as per the distribution. So how this parameter theta works? L will be written in the form of product of all this, right? The only difference here is that we have a product here because it is independent data. So whenever you have independent probability, if probability of A dot probability of B we were writing, if it is an independent event. So whenever it is independent data, we always take the multiplication. So L is called the likelihood function. So this notation I have introduced new here. This represents the product. Summation represent the sum. This represent the product. If you write product of xi, if you write this notation from I equal to 1 to n, this means I'm talking about the product. So we will get x1 into x2 into x3 and so on. Whereas summation of xi from I1 to n represent x1 plus x2 plus x3. Summation represent plus. This pi symbol is representing as product of xi from I is equal to 1 to n. So, all right. So if you can see here, you have f of x1 comma theta into f of x2 comma theta, so on up to xn comma theta. So this all product is represented with this symbol from I from 1 to n and xi comma theta. Then we will take log base e both side. If you take log both side, because it is product, your product will turn out to be summation. Log of this plus log of this, log m into log of n. So log of this plus log of this plus log of this. So log, if you take log both side here, this will turn out to be a summation we have seen previously. And this is called as log likelihood function. Because you want to maximize L, so we have to differentiate L with respect to theta. I have taken partial L here because you have two variable, two unknowns involved here. That is why I have taken partial derivative, two independent unknowns. So these steps are clear now, I guess. If any doubts in any step, please let me know. So we have already seen the example of Poisson distribution. This is in general case of Poisson distribution. So let me derive this quickly. So in this case, you have x1, x2 up to xn in general data. Previously, we have taken 5, 9, 3, 12, 14, some kind of data, and we have got some value of m here. So f of x comma theta is a Poisson distribution which will be represented as e power of minus m, m power of x by x factorial. So in this case, your theta is m parameter. So I will represent theta with m in this case. So I have to write the maximum likelihood function for m. So your maximum likelihood function will become the product of I is equal to 1 to n, because you have to write this term again and again for x1, x2, x3 and so on. So this will be product of e power of minus m. This will be m power of xi divided by xi factorial. So when you break this, you will get e power of minus m power x1 divided by x1 factorial into e power of minus m into m power of x2 by x2 factorial and so on. And the last term will be e power of minus m power of xn divided by xn factorial. So what we get here, your e power of minus m is multiplying up to n times. This will be e power of minus nm into m power x1 plus x2 plus xn you will get. So I will write this as summation of xi, and I will take this I from 1 to n whole divided by x1 factorial, x2 factorial up to xn factorial. So this is your likelihood function. Now I have to take the log both sides. So I have to take log L is equal to, this will be log of e power of minus nm into m power summation of xi minus log of denominator term. So this will be log of x1 factorial so on up to xn factorial. So now I have to differentiate this. So differentiate this with respect to the parameter we are finding. Here m is the parameter. So I will differentiate this. Before that, I will simplify this term. Log m into log n becomes log m plus log n. So this will be log of e power minus nm plus log of m power summation of xi minus this term as it is. So this implies minus nm log base e and e it cancels out plus summation of xi into log m minus log of x1 factorial and so on up to xn factorial, you will get it. So now I will differentiate this term with respect to m. So when I differentiate with respect to m, you will get minus n, m becomes 1 plus summation of xi into 1 by m you will get and minus 0. So when you take the differentiation of this equal to 0, because we are maximizing this likelihood function, so you will get minus n plus summation of xi by m is equal to 0. So when you write m value, you will get summation of xi by n. So we have seen this portion with the example previously. So we have got m is equal to 43 by m, which is nothing but your summation of xi, the data set which we have got, divided by. So you can derive any sort of maximum likelihood function and you can find any parameter of any distribution given to you. So like that, I have taken one more example of normal distribution. Gaussian distribution is another name of normal distribution. So in this case, you have f of x comma theta. And what is the normal distribution function? The normal distribution function is 1 divided by sigma root 2 pi, if you have not forgotten this, and you have e power of minus x minus mu whole square divided by 2 sigma square. Okay, so in this case, I am estimating mean. So I will take parameter as mean. Sigma, I'm not finding. You can estimate sigma, but in this case, I'm estimating mean now. Mean is the parameter for me. So I have taken theta is equal to mean. So what is the log likelihood function for this? So your L becomes the product of I from 1 to n, 1 divided by sigma root 2 pi e power of minus x become xi minus mu whole square divided by 2 sigma square. So if you break this, you will get sigma root 2 pi e power of minus x1 minus mu whole square divided by 2 sigma square. The next product will be 1 by sigma root 2 pi e power of minus x2 minus mu whole square by 2 sigma square and so on. It will continue. So the likelihood function here, you can see 1 by sigma root 2 pi, 1 by sigma root 2 pi is multiplying up to n times. So this will become your n times sigma root 2 pi. Then you have e power of this term into e power of this term. So e power will all add up, right? So I can just write this as e power of minus outside the summation I from 1 to n, and all this term will get add up. So this will be xi minus mu whole square divided by 2 sigma square, because e powers all will add up when you multiply. So now when you take the log, So you will get log of n divided by sigma root 2 pi into e power minus summation of xi minus mu whole square divided by 2 sigma square. So break this log m into log n. So this will be a log n divided by sigma root 2 pi plus, when you take log here, this will be log e power of this term. So whatever the power term will come first. So this becomes minus of summation xi minus mu whole square divided by 2 sigma square into log e base e. So log e base e always becomes 1, so I will just cancel this out. So now we have got the log likelihood function. Just differentiate this with respect to the parameter you are finding. So I will differentiate with respect to mu. So there is no mu term here. So this will be 0 minus, you have mu term here, but you have summation also given from 1 to n. So this will become 2 times summation of xi minus mu, 2 minus 1 is 1, into the coefficient of mu is minus 1 whole divided by 2 sigma square. So 2 and 2 get cancels out, minus 1 and 2 minus become plus. So this implies your differentiation of mu is equal to summation of xi minus mu divided by sigma square. Now you have to equate this to 0. So sigma square goes this side, becomes 0. So this will become summation of xi minus mu is equal to 0. So this will be summation of xi minus summation of mu is equal to 0. All right, we have this space. I just need a space, so I will just write down here. All right. Okay, so I will just take this term here. So this will be summation of xi minus mu is a constant term. When it come outside the summation, this will become n here is equal to 0. You are estimating mean, so minus mu, and you keep it here, and this will become minus of summation of xi. Minus minus get cancels out. So your mean is nothing but summation of xi by n. In this case also I am getting mean value as summation of xi by n, which is your maximum likelihood estimator. So